Here in this question, a small electric dipole P naught having a moment of inertia I about its center is kept at a distance r from the center of a spherical cell of radius capital R. The surface charge density being sigma is uniformly distributed on the spherical cell. The dipole is initially oriented at a small angle theta as shown in figure. While staying at a distance r, the dipole is free to rotate about its center. If released from rest, then which of the following statement are correct? Epsilon naught is the permittivity of free space. We need to find if the dipole will oscillate about this particular point or not, and if at all it does, then what will be the angular frequency? Well, the first option is dipole will undergo a small oscillation at any finite value of small r. Well, we know that inside the region of its spherical cell, the field will be zero, so dipole will not experience any force and it will not experience any torque. So option A will be the wrong statement. The dipole will undergo a small oscillation at finite value of r greater than capital R. At this point, the field due to this spherical cell will be along this direction, so the dipole will experience the force, but it is actually being written that it situated at this particular point itself, so it will have the tendency to rotate, and the dipole will rotate in a way that it will try to align along the direction of existing field. That means for this particular given situation, it will experience the torque along this direction. So I would say it will undergo small oscillation at finite value of r, that is greater than capital R. Now we need to find the angular frequency. Well, for that calculation, I would say let this be the point. The field along this direction will be E, that is Q, that is 4 pi capital R square into sigma divided by 4 pi epsilon naught R square. This is the field strength, and if dipole is placed along this direction, angle being theta, then torque it will experience, it will be how much? It will be P cross E. That means it will have the sine theta in magnitude. This is the value of P. So I would say torque restoring, it will be P naught. E will have the value of 4 pi will cancel out here, sigma R square divided by epsilon naught R square into sine theta. If theta is small, we can take this value to be theta itself. It must be equal to moment of inertia into angular acceleration alpha. So I would say alpha will be equal to P naught sigma R square divided by epsilon naught I into R square. It must be written as omega square into theta, or I would say omega to be equal to P naught sigma capital R square divided by epsilon naught I into small r square. Okay, here we shall see the option. Well, it is written in terms of the r to be equal to twice of capital R, and here it is equal to 10 of capital R. That means if r is equal to some integral value of capital R, then our answer will have the formatting as omega will be equal to square root of P naught sigma. I'm taking this value to be equal to small n into capital R, so this r square will cancel out and I will have it here as I naught I into n square. Putting the value of n to be equal to 2, I will have 4 in denominator here, and putting the value of n is equal to 10, I will have 100 in denominator. So clearly I can see that option D is the correct answer for this question. So what we are getting, option B and option D are the correct answer for this question. We can verify here on the sheet provided. Well, option B and D are the correct answer for this question.